Okay, welcome to Let's Get to the Marks. Here's a little quick one on halogenoalkanes. This is a question from the AS Chemistry 2023 paper 2. Um, let's get into it. Question 3. Question is about halogenoalkanes with hydroxide ions, their reaction basically. 3.1 outline the mechanism for the nucleophilic substitution reaction of 1-bromobutane with sodium hydroxide. First thing to do is highlight the key points, make a few notes if you need to, and have a go. So it's telling us we're using hydroxide ions here. It's telling us that it's nucleophilic substitution, and we've got sodium hydroxide. Let's get into this mechanism. So first thing to notice is our main reactant is 1-bromobutane. So let's quickly draw that out. Of course, it's butane and it's got a bromine atom on the first carbon. So just going to put that there for ease. Now I also want to highlight the electrophile. I've got sodium hydroxide, but of course it tells us it's hydroxide ions, and it's not an electrophile, it's a nucleophile. It tells us that with nucleophilic substitution. And this means it has a lone pair of electrons which it can donate, and obviously it's attracted towards positive things. So what's it going to be attracted to here? This is a nucleophile. What's it going to be attracted to in this molecule? Well, the carbon and the hydrogen are similar electronegativity, so not really there. It's going to be attracted here at this carbon, which is delta positive, and the bromine is delta negative. Now, you don't need to use these in mechanisms in AQA, but they're good for your understanding. And this means the lone pair from the hydroxide ion can be donated towards that delta positive carbon atom. Now, I just want to highlight some mistakes people make. Sometimes people draw the arrow and it appears to go towards a bond. A lone pair of electrons would be repelled from a bond, so never draw a arrow to a bond. For instance, to this one or that one, it's going to get you the mark taken off. Make sure it's going to that delta positive carbon. Now, because I've written the delta signs, which we don't need to do in AQA, this can make it hard for the examiner to see where it's going. So I should really be aware of that as well. I'm better off drawing this arrow going directly to that carbon from the lone pair, so the examiner is in no doubt of where I believe those electrons are going. I'm going to put the delta positive carbon sign down here. Good for our understanding of why the lone pair goes there. Now, I also need to show carbon is in group 4. It has 4 electrons in the outer shell, maximum 4 bonds. This would give it 5 bonds. One of the bonds has to go. It's going to be this bromine bond. So we draw the curly arrow from the bond because the pair of electrons in the bond are going to come out and go to the bromine. And that means our bromine is going to then have a lone pair of electrons and, of course, a negative charge. Now, if I needed to, I could show that as well. Now I'm just going to draw out the products here. You don't actually need to draw these out to get the marks. It just wants the mechanism, sort of first bit here. Well, the product, of course, is going to be an alcohol because nucleophilic substitution. And then we're going to have the bromine with the lone pair. And guess what? It's probably going to get together with that sodium ion that got left behind in the first part. But here I'm circling what you actually need to put to get the marks. You don't need to show the sodium ion. You don't need to show the products. And you don't need to show the possibility is that the sodium ions and the bromine ions will get together to form sodium bromide. You don't need to show that. Your 2 marks are gained by the mechanism there. Okay, let's move on to the next part of the question. So a student investigated the rate of nucleophilic substitution of halogenoalkanes with hydroxide ions. Identical concentrations of 1-bromobutane and 1-iodobutane were reacted separately with sodium hydroxide solution under the same conditions. So they've kept all the conditions the same to make it valid. The concentration of halide ions was monitored during each experiment. Figure 1 shows the results. We've got the concentration of the halide ions on the left, which are being released as the bonds are breaking, and we've got the time underneath. So we can see the reaction of iodobutane is higher, the line, than the one with 1-iodobutane. 3.2, state how figure 1 shows that the rate of reaction for 1-iodobutane is faster than the... And for the second mark, state why the rates of reaction are different. Right, well, first of all, we can see that 1-iodobutane is reacting faster. How can we observe that from that graph visually? Well, we can see that it has a steeper line, a higher gradient, so it's breaking down faster, okay? So that's the visual thing that tells us that 1-iodobutane is breaking down faster. Now state why this is happening. Well, if we look at the 2 bonds, we've got the carbon iodine bond and the carbon bromine bond in these haloalkanes or halogenoalkanes. And the reason some people think, oh, well, the bromine's more electronegative, is going to mean that you've got a stronger delta positive on the carbon. It's more likely to be attacked by a nucleophile. Well, actually, what it really comes down to is the bond enthalpy, and the carbon iodine bond has a lower bond enthalpy than the carbon bromine bond, so it requires less energy to break, i.e. it breaks more easily, or the carbon iodine bond is weaker. uh, Best answer is to say that the Ci bond has a lower bond enthalpy than the Cbr bond, so it's more easily broken. Thanks for watching, guys. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you in the next video.
You're still here? It's over.